quite often in the talks it disappeared, the sound. Is there anything particular that is?
Sometimes it is the cell phone.
Okay. I don't have one. So.
Does it work?
Yes.
You have a cell phone?
No.
Sometimes I don't know why.
Okay.
Depends of the day.
Yeah, no, but it's not. It's nothing with the cable that I can do something wrong, right? So I can just dance here.
I think you might want to put it a bit closer to the mouth.
Yeah. But if I'm talking now, I don't want to be booming.
Yeah, let me adjust for you. Here.
Like this? Yeah.
I put in.
That's good. Yeah.
All right, I think we can get started. My name is Igor Lizanowski. I'm from Nottingham. I'm hosting this first part of the afternoon. And without further ado, let's move on. And I'll hand over to our speaker, who is Rick van Bijnen from the University of Innsbruck. Is that actually technically correct? Or from ICOKI, I guess.
ICOKI.
Yeah. So, and he's going to talk about self-verifying variational quantum simulation of spin lattice models. Please.
Thank you very much. Well, first of all, I want to thank the organizers, of course, for giving me the opportunity to speak here at this wonderful location. Are we talking about some of our recent work, which is just on the archive? It's work done in a group of Peter Zoller. I'm a theoretician, but in close collaboration with the experiments of Rainer Blatt and Christian Roos. So, will be a mix of theory and experiment. So here we are talking about quantum simulation, and when we say this, we mean something which you could say is analog quantum simulation. So I go to the lab, I have some target model that I want to study, and I go in the lab and I really want to build this Hamiltonian, or I want to engineer the interactions, tweak all the lasers to get exactly this thing. So over recent years, we've seen some very impressive results. We have seen some very impressive results here at this conference. But still, I mean, you can always think of models, and there will always be very interesting models which are actually very hard to do. So if some condensed matter theorist comes up with some four-body ring exchange term or something like this, you have to work very hard to make this in the lab. So, and also maybe an opposite problem, right, that we have now. For instance, if I take the famous example of Rydberg atoms, then we always have this nice Hamiltonian here. And this gives rise to very interesting physics. But actually, if I look at condensed matter systems, then you typically have nearest neighbor interaction. So in here we have actually some power law tail, which can actually screw up the dynamics that you wanted to study. So sometimes you have a bit too much even. So another way of doing quantum simulation is digital quantum simulation. So here you take your Hamiltonian, you decompose it into little bits and pieces that you can do on your setup, and then you very quickly alternate these pieces, and in the end you mimic the effective action of the Hamiltonian. So, but for this you need typically you need almost universal gate set on a quantum computer, and this is also typically limited to short range interactions that you efficiently do. And even if you could do this, if you could solve all these problems, then there's always a sort of, in the future, there's always the problem of how can we trust the answers that these systems, that they produce, right? How do you know, if you cannot simulate it anymore on your computer, how do you know that these answers are right? So today I want to talk about let's say a third way of doing quantum simulation. It's called variational quantum simulation, which addresses these problems. So in a nutshell, what you do there is basically it's a hybrid classical quantum setup, where you have a computer which uses your setup as a sort of quantum processing unit. So it will take over certain tasks which are hard to do on the computer. For this you will use the quantum system, but for the other parts you will just use the strength of classical computers. So in this I will explain in a minute how it exactly works, but this is just to point out, this is ideas that came from quantum chemistry where they were developed, and also in optimization problems. So there's some nice papers here about it, but these are all for 2 or 4 qubits, like very small scale systems. And today I will show actually conditions under which we can do this for up to 20 qubits, so almost an order of magnitude more, or an order of magnitude more qubits. So this brings me to the outline of my talk. So first I will give a bit of an introduction of variational quantum simulation, show how we can prepare ground states of interesting models, how we can verify these answers, and then some entertainment and interesting things you could look at. So first the introduction. So before I say anything, I want to make very clear, in variational quantum simulation there's a very big distinction between the target that we actually want to study, so what model we want to study, and what quantum resource we have in the lab. These do not need to be the same at all, actually. So the target is just, in this case I will study spin Hamiltonians, which you can always, in its most abstract form, just write a sum of little Hamiltonians, or these are then strings of Pauli operators. So in the end I can write any spin Hamiltonian like this. And these are the type of models that I want to study. But this is totally general, so this can be a string of length 10. There can be arbitrary interactions between particles. On the other hand, we have a quantum resource, so we call it, that's going to be our quantum processing unit that we have in the laboratory. So here today I'll be talking about the ions of Christian Roos and Rainer Blatt, which can interact with some power law interaction, so they can tune it. There's a power here which can be between 0 and 3 roughly, and these interactions they can do very well. So they can do with very high fidelity. They can make the ions interact like this, and also with very high fidelity they can do single particle rotation, so they can flip spins and things like this. And in the end, what we will do with this, we will use this system here to produce highly entangled or interesting states, basically by just making quenches of these 2 operations. So these operations that we can do very well, entangling and single particle rotation. So typically we'll just run a sort of a quantum circuit like this. So we entangle them for a short time, do some single particle rotations, and then alternate. And this is actually the typical depth that we have. So it's really just only a very few quenches. And in the end, we want to create then states on this quantum platform which have something to do with this target that we want to study, right? So in the end, these 2 concepts here are then sort of brought together by the classical computer. So how does this work in practice? So here we have our computer, we have our target model, we have our quantum processing unit. And the goal is now basically to prepare here on this platform the ground state of our target model by simply minimizing this quantity here, so the expectation value of the Hamiltonian. So the computer, are these states here that I showed with these circuits, they are parameterized. So I can make the entangling operation act for a variable time. And I can also, of course, do the single particle rotations. I can sort of control the angles at which I want to rotate. So in the end, this state that I produce here is parameterized by a vector of parameters. Okay, so in this vector of parameters, we would just want to find the right one which prepares here the ground state. So it's really the classical computer starts with sending some parameters to the quantum system. The quantum system will prepare the state like this with the sort of a circuit that I just shown. Then it will produce measurements and give us back the expectation value of our target Hamiltonian for these parameters. And then the classical computer will look at the parameters and think, okay, let's try a new set of parameters. And it will send it again, and we go to the loop again, and this we iterate. So the measurement is actually, this is one very important part. So let's take here some sort of example spin model. Let's say for some reason I want to study this model, where I have sigma x interactions on side 3 and 5 and sigma z on other sides. And maybe some other, again, some arbitrary Pauli strings here. So it's there's 2 terms here in this Hamiltonian that I want to study, or maybe more. So what we do now is first, the classical computer asks basically the experiment, what is the expectation value of this thing, and this thing alone? So we'll send the parameters to the experiment will prepare the state, and then we just measure the particles that we have in the right basis. So I measured particles 1 and 2 in the z basis, particles 3 and 5, which are here, I measure in the x basis, and the other ones I also measure in the z basis. So here I just get a single shot now. This gives me some value for this term here. Send it back to the computer, and actually I do this many times. So if I do this many times, in the end I'm building up the expectation value of this first term of the Hamiltonian. So it looks kind of like this. There's many shots, and in the end we have collected enough data to have a good idea of what is this H1. And then we can move on to the second term. So at no time do I have to have these terms or this Hamiltonian present in the lab. So I don't have to make this term and this term in the lab. These are non-commuting. But I just have to measure the right correlation function. And in the end, from all these measured correlation functions, I can build up the total expectation value of the Hamiltonian. So the Hamiltonian is never made, it just exists as a measurement recipe of what do I need to look at to give me this quantity. So, and this is just one expectation value for one set of parameters. I have to do this many times. So, and then in the end, if we have all these expectation values, then we can start, the classical computer can run an optimization algorithm to try and figure out what are the best values for this. So in a very short summary of what I've just told you, is we have a classical quantum feedback loop. The quantum system does the quantum part, so it produces expectation values of operators. And this way we can actually, in the end, construct ground states of our Hamiltonian in the lab. And there's we never have to realize the Hamiltonian. So this is very flexible. So any model, any spin model you can think of, which has this format, you can just immediately prepare states. And we use here now ions with this interaction, but this actually works for any platform where you have basically some entangling operations and some general single particle rotations, and where you can measure at single sites. So this would work actually for a lot of platforms. Yes. Yes. Well, so first of all, if there are systematic errors, it's fine, right? It's just about if I can produce states here, whatever the state is, as long as it's reproducible. So in the end, what comes out, if the expectation value of the energy matches the ground state, there's no other choice than having the ground state in your experiment. You will really have it. If there is noise on top of it, it will in principle average out. You probably have to measure more, you have to do more repetitions, but I would say it averages out, and then you have up to a certain fidelity, limited by your noise, you can say that you have the ground state. Okay. Yeah, sure. This is a matter of controllability. Can I reach the state? Okay, yeah. I can say something at the end. So, okay, so just a bit of advertisement. So in Innsbruck, so how does this look now in practice, in our experiment? This is the map of the campus in Innsbruck. And there's actually 2 experiments that we have, 2 ion experiments. So we have here the university building where we have a digital quantum simulator. We have seen something, I guess, last week by Philipp Schindler about this. And here at the Institute for Quantum Optics, we have an analog quantum simulation, so the system I just showed. And actually that's also where we are, the theoreticians, with our little computers. And actually it's really like this. We have written code that does this variational state preparation, and there's just a flag there that you can set to false, which means we simulate it. And if we set it to true, we don't simulate it, but we get the answers from the experiment. So it's really just one bit that you flip, and we are really doing this, and we're using this experiment as a quantum processing unit. So I will just be talking about this one. Okay, so that's the idea of variational quantum simulation. So I'll show you now the preparation of ground states of a spin model with 20 ions. So and the target that we choose is the Schwinger model, which is a model of quantum electrodynamics in one dimension. So here we discretize a 1D universe, so there are sites where there can be electrons or positrons. We encode this as spins, and we have a sort of a funny encoding here. It's a Kogut-Susskind encoding where you distinguish between even sides. So there on an even side, if the spin is up, we say there's no particle. If the spin is down, we say there's a positron. On the odd sides, actually the definition is the other way around. If the spin is up, there is a particle, an electron in this case. And if the spin is down, there's nothing. So for the here example here, we would have positron, nothing, positron, electron, etc. So the Hamiltonian that you get from this looks like this. I'm not going to say too much about it. I just want to point out what the individual terms do. So first you see here a term which is an exchange interaction. So the two spins, they flip the state. So actually if you look at this encoding and then you see what it does is actually it's creating pairs or annihilating pairs of electrons and positrons. Then there's a term which is just the mass, so the actual rest mass or the energy associated with having a particle in the first place. There's a -1, it's alternating because of this alternating definition. And then the final term is basically, because these are charged particles, there's electrical fields in here, and so there's an energy associated with a certain charge configuration. You can calculate this using Gauss' law, the total energy here. But you see, actually, I have not written here, but this is actually a very long range interaction. So it's really all to all with a very specific strength, because if I want to know what's the field energy here between these two particles, so basically I need to know what all the other particles, what their states are. So this would be the tough part to make if you want to really do quantum simulation. This is very difficult to realize in an experiment. So finally I want to point out actually what's important later is that this model has some symmetries. So the total magnetization is conserved, obviously, because this is just an exchange and these are sigma z's. And there's also in the magnetization zero sector, which is the one where we're interested in, there's a C symmetry. So that means that if I flip my system like this and I flip everything upside down, then I'm back at the same state. So this was the target, right? So I told you before, there's a big distinction between the target and the resource. So the resource is the ion platform that I already discussed, where we have interactions that we can do very well, and we have single qubit rotations. And then the one extra modification that we do is actually we make sure that the interactions actually turn effectively into an exchange interaction, so that we automatically conserve the magnetization of the system. And also any single qubit rotations that we do, we make them CP symmetric. So we conserve all the symmetries of the model also in our ions. So basically if this is our Hilbert space, then our symmetric subspace is kind of here, and we make sure if our final answer is in this space that we sort of keep only constrained to this space. And the final thing is that if you have very long strings of ions, then in the middle you don't expect to see much from the boundary, so we use a bulk symmetry. So the single particle rotations in the middle, we kind of group them all together, so there's just one control angle for the middle few particles. Okay, so that's the resource. Then finally I can briefly say something about the computer, because now the computer has to somehow optimize this thing. So for this we use a classical global optimization algorithm. So the problem is actually, it's pretty difficult, right? There's a global optimization problem. We found there's typically many local minima, so it's a difficult one. It's noisy because I get my information from the system from projections. So I do projective measurements and preferably very few of them. So I get very noisy energy values. We don't have gradient information. So it's a very hard optimization problem actually. So in the algorithm that we use, it's called the direct algorithm. It's the dividing rectangles. Maybe in view of the time, I will skip through the details. Okay, so now we're back at the campus in our building. The experiment is ready, the computer is ready, we have our optimization algorithm, we have our Hamiltonian here. We can set the flag to true, so we really want to use the experiment for our answers, and we can go. So the quantum circuit, just to give you the numbers actually, so I have 3 entanglers in total, so it's precisely this, but then with 20 ions. There's 3 rounds of single particle rotations, and we use a bulk symmetry on the central 12 ions. So this is then what a typical experiment would look like as a function of the iteration number. So how many times do we ask the experiment for an expectation value? And these are the energies. And you see actually here, you see a lot of points all over the place. And this is because we are using a global optimization algorithm. So it's not what you usually expect where you see only something going to 0. It's like it keeps exploring all over the place. Because you want to do a global optimization. So if you have not looked somewhere, you don't know if this might be a better place. So in the end, you have to look everywhere. And that's what's happening here. So in the end, if I can plot here now the theoretically calculated ground state energy and the first excited state, and you see actually the algorithm is really, it's getting there, right? So we can calculate an estimate of what the ground state energy is from all these measurements. You can sort of make a prediction of what is likely to be the lowest energy and the best state, and then you see this prediction actually approaches the ground state pretty well. And also, okay, you see here a lot of iterations. You think, okay, I have to do 1200 experiments for this, but just for 15 variational parameters, if you just consider the size of the space where I have to find my answers, right? If it's 15 dimensional, if I would just make a coarse-grained division of the space, where I divide every axis in 10 steps, then I have to do 10 to the 15 parameters to just get a rough estimate of the space. So then if you think, okay, in 10 to the 3, it's actually pretty efficient. Yes? It's 30 shots per measurement basis. So for the Schwinger model, we have to measure once everything in the x basis, once everything in the y, and once everything in z. So it's 90 shots per point. It could be less actually. The algorithm is such it could also be just 6 shots, but just there's some technical overhead. If you do 6, you might as well do 30. So let's do 30. Okay, so then, okay, you see we approach the ground state, but then you want to know, okay, how good is this now really, right? So, yeah, that's projection noise. So it's just, I mean, I have strings of Pauli products. They're always plus or minus 1 in the end if I evaluate a string. If I just take 30 of them, just because of fluctuations, you will go below. If I would take more shots, if I would take 300, this would happen less and less. It's impossible. Okay, if your measurement is perfect, right? So if your measurement, if you're not measuring exactly along x and y, so if your measurement axes are not exactly orthogonal, that's a different question. But if your measurement is perfect, then there is no way. I mean, if I evaluate the energy of a state, there's no way it can be better than the ground state. It just cannot happen. No, it's impossible. It's just impossible. There is no state which has a better energy than the ground state, right?
No, but sorry, can you just interpret this as just an error bar? Like when I do variational calculations, sometimes I have results which are lower than the ground state. But because I have an error bar, and I think here you have the same statistical.
No, the error bar only comes from the shot noise, from the projective noise. Only, I mean, you cannot make a state which has an energy lower than the ground state. Yeah, that's just for reference. I mean, in principle, you don't know this, right? Yeah, just a simulation, right? So for 20, I can just about do this. So. Hmm? Exactly, yeah. Actually, so these points are there for a given set of parameters, and actually it often repeats. So it's not 1200 unique points, but sometimes, actually here you see, this is a zoom in of a slice here, you see the error bars. You know, and sometimes the algorithm has to decide, is this point now better than this one? You don't know, right? Because there are these error bars, so actually then it will revisit the point, take some more, reduce the error bars, and then you will typically see that the point just would move up. Yeah. They are actually, I did not explain it, but they are the distance in parameter space from the best final point. So it's something you do after the fact. Actually, it's just for visualization, but okay.
Okay,
Cool.
I suggest we move on. Right?
Yeah, exactly. Yeah, sorry.
Obviously, you can talk a little bit longer now.
Yeah, I will. Okay, so now how good is it actually? So we can still do the simulation just by setting the flag to files. We can compute the overlaps. For the plot that I showed you, it goes to 80%. Actually, in the last week, we've been measuring a bit longer, and we reached finally 85% overlap. But of course, this is only by doing the simulation. So as I said in the introduction, there's a problem with verifying the answers, right? So in the end, if I cannot do the simulation anymore, I would also want to know how good is the answer. So for this, we go back to our target. I wrote here an arbitrary spin Hamiltonian. But I can also just take my Hamiltonian and square it. I mean, if I square it, in the end, it's still of the same form. I just get still Pauli strings here that are just twice as long, more ugly, but in principle, it's the same thing. So we can measure it. So this means we can actually measure the variance of the Hamiltonian for the state that we prepared. So if you know if this variance, if it's 0, you know you are in an eigenstate. So we can do this for the Schwinger model. I do it here for 8 ions because yeah, you have to do a lot of measurements. Where we had 95% theoretical fidelity, and we just select some points here, and we measure this quantity. And then we see that this quantity in the end, it goes close to 0, not entirely. This is actually the energy of the gap, so it's an energy, or it's squared energy. So the energy of the gap, and you see you go below it. So what these points means actually, so this variance, this means actually, this tells you how far away am I from a real eigenstate of the system, at most. And this is measured on the device itself. So you don't have to do simulations, this really tells you the energies that I get out of this procedure. I know for sure on the same device, I know how good they are. Okay, then very briefly, just to show you, I mean, in the end now we've prepared states, but you actually have this state in the lab. Even though I don't have the Hamiltonian, I have the state, so I can also measure other properties that I want. So for instance, you can observe a phase transition, which is present in the Schwinger model. So if I would be able to vary the mass of the particles, then you see if I have a very large mass, it's very expensive to make particles, so I would just have an empty universe. If the mass would be very large and negative, it's very favorable to have particles, and we get a full universe. So in between it transitions between these two states, and we can just take different masses, do the variational optimization there, and then you really see that if I evaluate this order parameter on the states that we have, that you can really track this thing. In view of the time, I will wrap up. So I've explained to you variational quantum simulation, which is a very flexible method of realizing spin models, which you previously probably would have thought you would never be able to do in your lab. It uses whatever quantum resources you have. You just have to be able to prepare certain states in there. Well, you saw already, I showed thousands of experiments with 90 shots each, so it's obvious your experiment needs to be fast. This really builds on the fact that, okay, in modern day experiments, they become faster and faster and faster. For the ions, we have a 30 millisecond rep rate. So when we really use this, the fact that we can do so many experiments so fast, we really use this luxury by just running this computer then on this thing. And then the nice thing is that the answers that you get out, we can actually verify how good they are. And this is maybe for the discussion, we also have some indications that this will be scalable for interesting problems. So when you want to go beyond 20 particles. So. Okay, just quickly, the Innsbruck Quantum Cloud. Just to point out the people that were most important in this work. There's Peter and there's then Christian Kokail, the PhD student from the theory side working on this. And on the experimental side, it was Christine Meyer who did most of the experiments. So with that, I would like to thank you for your attention.
Thanks a lot, Rick. Are there more questions?
Rick, so suppose that you were able to project out the ground